So unlike a normal photograph, a digital image is made up of pixels, small individual locations of a certain colour or a certain level of grayscale intensity, and we store that in memory as basically a very long list. And along with other information like the width and the height of the image, we can then access those pixels and determine what colour they are, and what we can then do other things like apply our filters or compile them into a video or something like that. So to keep it simple to begin with for a demonstration, we'll talk only about uncompressed images already loaded into memory. So rather than a specific file format like a GIF file or a BMP file, we'll talk about them some other time. We'll talk just about uncompressed images in memory, how they are stored and how we use them. Usually memory is a contiguous block, so it's all one long line, and so it's very helpful to us to represent two-dimensional images as actually a very long line of data. So what we usually start with an image is some kind of header, and that will tell us what the image file format is, how wide it is, how tall it is, and if there's any other information like EXIF data or camera calibration data, that sort of thing will be included in there. And then we essentially have a very, very long list of pixels. So we start here, and this point here will be our first row of our image, and we'll have a pixel here we'll call pixel 1, and then we'll have another pixel here, pixel 2, and how long each of these pixels is in memory will depend on the type of image we're looking at. So if we're doing, let's say, a 2x2 image, then our image will look a bit like this when it's finished. Pixel 1, 2, 3, and 4. So this is our image. It's 2 pixels high and 2 pixels wide. So in our actual memory, we have our header, and then we have the first pixel and the second pixel, so that's row 1. And then we might have some padding data that we won't worry too much about, and that depends on the file format. And then we'll just go on straight onto our second row. So we have pixel 3 and pixel 4. And that is essentially our image stored in memory. And then because we know how wide and how high the image is, we can index these directly. So we can say that if this is our stride, which is 1 plus 2 plus p, then we can go 1 stride along to get to the next row, and then 2 strides along to get to the next row, and so on, and we can read the image like that. So that's what an image looks like on a very basic level. Each of these pixels represents some amount of memory. How much that is depends on the type of image that we're looking at. So if it's a grayscale image, generally speaking, there'll be less memory used than if it's an RGB image. RGB images are by far the most common. Most images that we capture are RGB.
And RGB is red, green, blue, yeah?
Yes, red, green and blue. And they represent the primary colours that we detect in our eyes. So that's why it's helpful to think of them like that. A couple of extra properties of our image that we look at is the bit depth. And that is how many bits, how many noughts and ones represent each individual element of colour or grey, and a number of channels per pixel. So that in an RGB image that might be 3, or it might be 4 if it's an RGB alpha image.
And that's what
alpha is transparency. So a pixel will have a number of channels, so let's say C in this case is 3, so for RG and B, and then the bit depth is usually 8. You can get bit depths ranging from 1, which was just an 0 or 1, so the pixel is either on or off, up to 16, maybe 32, that's very high. Just like with normal binary encoding, the more bits you use per pixel and per colour channel, the more information you can hold. So 8 is a maximum level of 255 for a byte. And so in this case, we have 3 channels, R, G and B, each of which can be somewhere from 0 to 255.
What would those numbers represent? So 0 would be what, black and...
Yeah, 0 would be none of that colour at all. And 255 would be the most of that colour that the camera's seen, bearing in mind that some sort of processing will have taken place because of ISO and things like this.
And then so all that you do when you're increasing the bit depth is giving more different increments in between?
Yes, that's exactly right. It's unlikely that you would use it to show even brighter red, because usually 255 would mean as red as you could get, let's say. So you would just have a finer range of colours in between. For most general purpose use, a bit depth of 8 is perfectly adequate, because you've got 3 different colour channels doing that, so that's perfectly ample. So another common file format would be an 8 bits per pixel grayscale image. So if you go into an image processing package and you take your colour image and you convert it to grayscale, what it usually does is some averaging of the 3 colour channels, and then a much more memory efficient way of storing that would be to represent it as grey. So in that case we have our header information, and then we literally have pixel 1, which will just be a grayscale value from 0 to 255. So we'll have a byte here, which is pixel 1, and a byte here, which is pixel 2, and a byte here, which is pixel 3. And each of those only takes up 1 byte rather than 3 or 4 for a normal RGB image. And that's why RGB images are generally much larger. So alpha is very common when you're doing image editing. because it might be useful for sort of combination of layers above other layers and things like this. It's obviously not very common in normal photographs because camera can't measure transparency, it wouldn't make much sense. But in general, 32-bit images, that is 4 channels per pixel, is very common, even when we're not using the alpha. So you might find that your digital camera produces a 32-bit per pixel 4-channel image, even though it doesn't actually output transparency, and that alpha is just held as a padding byte. And that way, we can index each of our pixels in integer terms, and it makes it much simpler to do the mathematics of getting to a certain pixel and doing something with it. If this is our header and this is our colour image here, then what in fact P1 is a row of RGB and then possibly an alpha channel or possibly something that doesn't do anything. So we'd have the red here, the green, the blue, and this X here, which may be an alpha channel, may not be. And each of these in an 8-bit image will be 8 bits long. So that's 1 byte. So this is 8 bits long, this is 8, this is 8, and this is 8 here. And then so the total size of this pixel is 32 bits. And that's what 32-bit image is. Now, 32 happens to be, on a lot of computer architecture, the size of an integer, or at least if it isn't, you can get a 32-bit integer very easily. And that allows us to jump to a specific pixel somewhere in our image. So the height of our image is useful for knowing when we're going to go off the end of the image and into some other memory. But in terms of indexing pixels, we don't use it. What we use is something called a stride, which is the width of a row of an image, bearing in mind any padding, and that depends on the file format. So
would it be fair to say that the height of the image is however many strides you've got?
That's exactly right, yes. But of course you're looking at a single block of memory, and if your operating system isn't being careful, you want to make sure you don't go off the end. If we know what our stride is here, and that will be some width in bytes of our image, including any padding. And then we know we have a variable x and a variable y that tell us which pixel we want. Then where we want to go to is the very beginning of our image, plus a certain number of rows based on our y, plus a certain number of pixels based on our x. So the actual formula is the pixel we want is y times the stride plus x. And that will take us through a certain amount of rows of data and straight to the row we want and then to the pixel we want. And so this formula we can use to jump straight to the pixel we want. And then using some slightly more advanced programming and bit shifting, we can obtain the actual RGB data out of that integer. And then we can do things to it. We could average them to make it a grayscale image, or we could blur them, or we could add an alpha channel if we were doing some kind of more complicated image editing, something like that.
Obviously, I'm using image manipulation to make these computer file videos all the time. So if I'm selecting a pixel in Photoshop and deciding to, I don't know, change it in some way, this is what's going on behind the scenes.
This is exactly what's going on behind the scenes, yeah. So it will, if you select an individual pixel, it'll know the X and Y location, it will know how that image is stored in a big row in memory, and it will index that location and alter the RGB values for you, which makes it a lot easier. If we want to turn these into pixels, all we need to do is to look by the nearby pixels that have the colour we're looking for and interpolate that value. So in this case, we don't have a green value here, but we know what this green value is, and we know what this green value is.